Hi everyone. Today we are going to continue the chapter 11, the part B portion, where we are going to discuss about the certain terms of the voltage, electricity, as well as how an action potential is generated and propagated, and some of the clinical aspects of it. So, what is membrane potential? Like all cells, neurons have a resting membrane potential. Uh, the difference between that, the resting membrane potential of the neurons can be changed very rapidly. And because of that, neurons are highly excitable cells. Let's discuss about some basic principles of electricity. So with related to the electricity, there are two types of charges, positive and negative. So opposite charges are attracted to each other. And energy is required to keep opposite charges separated across a membrane. And also, when the charge ions moves toward one another, energy is liberated. And when opposite charges are separated, it's said to be the system has a potential energy. So let's look at some certain terms. The first one is the voltage. The voltage defines as a measure of potential energy generated by separated charge. So it's been measured between 2 points, and the measuring unit is volts or millivolts. So voltage, with related to the physiology, with related to the nervous system, we call it as the potential difference or potential, which also means as the charge difference across the plasma membrane, and that results a potential. So the greater charge difference between the 2 points, higher the voltage. The next one would be the current. The current defines as the flow of the electrical charge or ions between 2 points. And the flow is dependent on a current, is dependent on voltage and the resistance. And we can put them into an equation, which we are going to see later. The next important word is the resistance. The resistance is the hindrance to a charge flow. So, different components provide different resistance, such as the insulator, which we refer to as the substances with high electrical resistance. They have a higher hindrance to the charge flow. Conductor, they have low electrical resistance, so the current flows or the charge flows very easily through conductors. Considering all these terms, we can find a relationship between the voltage, current, and resistance, and that is been described by Ohm's law. So the Ohm's law gives the relationship of the voltage, current, and resistance, where the current is equal to the voltage divided by resistance, which means like the current is directly proportional to the voltage. That means the greater the voltage or the potential difference it would be. There's important fact where there's no net current flow between points with same potential. For instance, if it has 70 volts and in one point and another point is as 70 volt, the difference is 0. So there is no net current flow between those 2 points. Current is inversely proportional to the resistance. As you can see, the current is inversely, the R, the resistance, is below the V, which is the greater the resistance, the smaller the current would be. And it explains if you have high resistance, there is less flow of charge. The basic principles with electricity and with related to the membrane potential is that there are certain functions that the membrane ion channels do to create the membrane potential. So let's go to the very basics we have talked about when we discussed the plasma membrane in earlier chapter, but we have to recall what we have learned before, and then we need to understand how it's been generated. The action potential is generated in here. So the role of membrane ion channels. The large proteins, of course, we know that they made these ion channels. They serve as selective membrane ion channels. For instance, if it is a potassium ion channel, it only allows potassium to pass through. There are two main types of ion channels. Leakage, we also call them as non-gated channels, which are always open. The gated ones is in which part of the protein changes to its shape based on the stimuli, or it could be closed based on the stimuli. So there are three main gated channels. They are chemically gated, voltage gated, and mechanically gated. So the chemically gated ion channels, we also call them as ligand gated channels. They open only when binding of a specific chemical. For instance, if it's a neurotransmitter, such as the acetylcholine, those ion channels open up when only the acetylcholine bind to that channel. The voltage-gated channels, they open and close in response to the changes in the membrane potential. The mechanically gated channels, they open and close in response to the physical deformation of the receptor, such as in the sensory receptors. So the mechanical gated ones, the conformational change has to happen for that ion channel to be open or close. So in these figures, it shows the chemically gated ion channel and the voltage gated ion channels. For instance, as we discussed, the chemically gated ion channel, the channel is being depicted here. It's been closed in this, the first figure, when a neurotransmitter or chemical bind to its receptor, the ion channels opens up. With related to the voltage-gated ion channels, if you would see the membrane potential outside is plus, inside is minus, and the membrane voltage changes where it changes outside into negative or minus and inside into positive, the ion channels opens up. More about the gated channels. When they're open, the ions can diffuse quickly, either inside or outside. And it happened along the chemical concentration gradients from higher concentration to a lower concentration. When there's the word called diffusion, you have to remember it's always from higher concentration to the lower concentration. It could also go along with the electrical gradients, which is toward the opposite electrical charge. The ion can flow towards the opposite charge due to the attraction to each other. The electrochemical gradient, it's the electrical and the chemical gradients combined. Electricity, chemical, the chemical component play a role. The ion flows creates an electrical current and voltage changes across the membrane. And as we have discussed before, It can be expressed by rearrangement of the Ohm's law equation. Initially, it's I equals V divided by R. Now it's voltage equals the current as well as the resistant. So let's look at the generation of the resting membrane potential. Physically, the resting membrane potential can be measured with a voltmeter, and it measures the potential charge difference across a membrane of a resting cell. In a resting neuron, the resting membrane potential is approximately minus 70 millivolt. Inside the cytoplasm, the cytoplasmic side, the membrane is negatively charged relative to the outside. The actual voltage difference could vary from minus 40 millivolts to minus 90 millivolts. And at this millivolt range, we said that the membrane is polarized. So the potential is generated by two different things: the differences in the ionic composition of the intracellular fluid and the extracellular fluid, and differences in the plasma membrane permeability. So this is a figure which shows how it's been measured with a voltmeter. You can set up an electrode outside of the cell, and you can insert a microelectrode into the cell, and you can check the differences where you receive the resting membrane potential. So let's look at the first part, the differences in the ionic composition. The extracellular fluid has higher concentration of sodium ions than the intracellular fluid, and this is being balanced chiefly by the chloride ions. The intracellular fluid, of course, it has higher concentration of potassium than the extracellular fluid, and the balance is being balanced by the negatively charged proteins. So potassium, by the way, play a most important role in membrane potential. So this could be a very good multiple choice point, where if they ask like, what is the most important ion with related to the membrane potential, it's the potassium ions. So let's look at step-by-step process of generating a resting membrane potential. And the resting membrane potential depends on the differences in the potassium and sodium ion concentrations inside and outside of the cell, and the differences in the permeability of the plasma membrane to these ions. So this figure shows the differences between the ionic composition outside of the cell, where the sodium amount is high and the potassium concentration is high in the inside of the cell. And one of the pumps, that is the sodium-potassium pumps, maintain the concentration gradient of the sodium ions and potassium ions across the membrane. So the other important fact is the differences in the plasma membrane permeability, and let's look at a little bit of in detail about that. The plasma membrane is impermeable to large anionic proteins, but it's slightly permeable to sodium ions through leakage channels, where the sodium diffuses into the cell down the concentration gradient. However, the potassium is more permeable, that is 25 times more permeable than the sodium, and therefore the potassium diffuses out of the cell down the concentration gradient. The plasma membrane is quite permeable to chloride ions, and that's it balance the differences. How we are going to establish a resting membrane potential? The very important steps are more potassium try to diffuses out than the sodium diffuses in. And as a result, the inside of the cell become more negative, and this establishes the resting membrane potential. The other important key aspect is that the sodium-potassium pump, where once the resting membrane potential is created, it stabilizes this resting membrane potential. So that's why I highlight the word stabilizes, because that's what the sodium-potassium pump does, which means like it maintains the concentration gradient for sodium and potassium. How? It pumped out 3 sodium from inside to outside, while 2 potassium is pumped back into the cell. So if you look at this figure carefully, it will show again much more in detail about how this ionic composition changes and what would happen with related to ionic changes and how it relates to the resting membrane potential. And it's been clearly described nicely, so you can go over these important facts. Then let's talk about what will happen with changing the resting membrane potential. Membrane potential changes when 2 things change. That is, the concentration of the ions across the membrane, as well as the permeability to those ions change. The changes produces 2 types of signals, that is, the graded potential as well as the action potential. The graded potential, the incoming signals operating over a short distance, and action potential, they act for long distances. The changes in the membrane potential are used as signals to receive as well as integrate and send information. There are certain terms you need to understand with related to the resting membrane potential as well as for any description of membrane potential. So these terms are used relative to the resting membrane potential. The first one would be the depolarization, that is, decrease in membrane potential, the resting membrane potential. Of course, now we know the resting membrane potential of nerve is range from -40 to -90 millivolts, and we will think like it's 70 millivolt, the average. So what does depolarization does is that the -70 is going to move up, which is it's going to go closer to -70, turn into -60, then -60 into -50, then 0, and then it can go into plus sign. With related to the depolarization, inside of the membrane becomes less negative, because for a minus to become more positive ions needs to come in. So the membrane inside is become less negative than the resting membrane potential. And this depolarization has a probability of producing impulse increases. The next important word is the hyperpolarization, that is increase in membrane potential, that is more away from 0. So we'll say thinking of minus 70 millivolt, it's going to be minus 90 millivolt. It's go more negative. In this case, inside of the membrane becomes more negative than the resting membrane potential, and probability of producing impulse decreases. So this figure shows the depolarization and hyperpolarization of the membrane, which have been showed in a voltmeter, where with the depolarization with the stimulus, the minus 70 starts to move towards minus 50, that is more towards the positive side. It's less negative. Here with the hyperpolarization, you would see minus 70 go further down, it goes closer to minus 70 or minus 80 or minus 90. Since we encountered the word graded potential and action potential, let's look those two. What is graded potential? It's a short-lived localized changes in membrane potential. The stronger the stimulus, the more voltage change is going to happen and farther the current flows. It works for short distance that we discussed before. The triggered by stimulus, which opens up the gated ion channels, and that results in depolarization or sometimes hyperpolarization. And the graded potential can be named according to the location and the function. And it could be two types: receptor potential, which is the graded potential in the receptors of the sensory neurons, are called as receptor potential, and postsynaptic potential, neuron graded potential. So here it will show the spread and the decay of the graded potential. It's a short-lived, that quick depolarization is happening at this area. The inside become positive and it could dies off. Once the gated channels opens, depolarization spread from one area to the membrane to the next one, a very short distance, and then the adjacent area is going to be depolarized, and opposite charges going to attract each other, and it creates a current as shown in this figure. And how it degrades, the current flows but dissipates quickly and decays. So that's why when we put it in a graph, the resting membrane potential, it's a short-lived depolarization and then quickly go back into resting membrane potential with a few milliseconds, and it's been for very short distance as shown in this figure. What is very important is the action potential. The action potential is a principal way where neurons send signals. It means like long distance neural communication. It occurs only in muscle cells and axons of the neurons. Brief reversal of membrane, it's a brief reversal of membrane potential with a change in the voltage of minus to minus 70 millivolts and shoots up to closer to plus 30 millivolts, which is a difference is almost approximately 100 millivolts. The action potentials, they do not decay over distance as graded potentials do. That's a difference between graded potential and an action potential. The action potential in neurons is referred to as a nerve impulse, and also action potential involves opening of specific voltage gated channels. Generating of action potential, we can divide them into four major types: the resting state, depolarization, repolarization, and hyperpolarization. In the resting state, all gated sodium and potassium channels are closed. Depolarization process, sodium channels open up. That is the main ion channel with related to depolarization. These are very good MCQ points. Repolarization, the sodium channels are inactivating and the potassium channels are open. And hyperpolarization, some potassium channels remain open and sodium channels starts to reset. With related to the resting state, let's look what's going to happen. So in the resting state, all gated sodium and potassium channels are closed. Therefore, only leaky channels for sodium and potassium are open and they maintain the resting membrane potential. Each sodium channel has two voltage sensitive gates, that is activation gates, which is closed at the rest, and these activation gates open with depolarization process, and that will allow sodium to enter the cell. The inactivation gates, they open at rest. So once it is open, it blocks the channel to prevent more sodium from entering the cell. So don't get confused. The inactivation gates open at rest. The activation gates closed at rest. So here it shows that ionic change with related to the depolarization process of the voltage gated sodium channels as well as the potassium channels. So at this stage, the sodium channels closed at the resting state, so no sodium enters the cell through them. And with related to the depolarization process, it's opened by depolarization and sodium ions comes in. And in the inactivated channels, automatically blocked by inactivation gates soon after they open. So these are the activation gates which opens up the inactivation gates at the resting state. They closed. With related to the potassium channels, they have one gate and two states. So closed at the resting state, potassium ion channels. So no potassium exists through the cell, this voltage gated potassium channels at the resting state. And with related to the depolarization, they opened up and allowed potassium to exit the cell. That is a very slow process compared to the sodium channels. So each potassium channel has one voltage sensitive gate, sodium has two gates, potassium have one gate. Potassium channels closed at rest, they open slowly with the depolarization. So that's why more sodium comes quickly inside with the depolarization process. This is again the same picture in much more bigger view. Yes. So with related to the resting state, all gated sodium and potassium channels are closed. So that's why you don't see a spike over here at the resting state with this action potential graph. So what will happen with the depolarization? The sodium channels starts to open up. The depolarizing local currents open voltage gated sodium channels and sodium rushes into the cell. This is a very quick process. And therefore, sodium activation and inactivation gates open. Sodium influx causes more depolarization, which opens up more sodium channels. And therefore, the intracellular fluid becomes less negative. Minus 70 goes to minus 50 and then minus 40 like that. And at the threshold where it's around minus 55 to minus 50, positive feedback makes opening of all sodium ion channels, and lots of sodium comes in at the threshold level, which results in a large action potential spike. And therefore, the membrane polarity can jump to positive side, plus 30 millivolts. So that is what is being seen here. At the threshold level, where it's around like minus 55 to 50, positive feedback leads to lots of sodium channels to open up. Sodium gushes in, and then the membrane inside become more positive, which is less negative, and then the voltage spikes is seen in the action potential graph. With related to the repolarization, the sodium channels are inactivating at this point, and potassium channel starts to open up. Once the potassium starts to open up, sodium starts to go out. That is, positive ions are leaving from inside. Therefore, the membrane starts to go back to negative back again. And this potassium exit happen according to the electrochemical gradient, and repolarization process returns the resting membrane potential, bring back the membrane potential into the resting membrane potential. And this is what we've seen in this case. Here, sodium ion channels closed up, the potassium ion channels open up, and potassium moves out, and then the membrane potential starts going back to resting membrane potential. With related to the hyperpolarization, the important fact is some potassium channels remain open and sodium channels resets again, but because some potassium channels are open, further positive ions are moved out, so membrane potential goes a little bit more negative than minus 70, and with the resetting of sodium channels later, it brings back to the resting membrane potential. So sodium channels, that's why it said it resetting back to membrane potential. So here you would see the resting membrane potential here. In the hyperpolarization, it goes a little bit below that, the resting membrane potential. So keeping up, because the potassium, some of the potassium channels are kept open, more potassium loose, and then later with this little increment, the sodium channels play a role to reset the membrane potential, bringing back into resting membrane state. Yes. So here it shows all the four steps that we have discussed: the resting state, depolarization, repolarization, and the hyperpolarization process. So how does the action potential generated? Continuing the facts, the repolarization resets the electrical conditions, but not the ionic conditions. So after repolarization, then the popular pump, sodium-potassium pump, jumped into play a role, which it restore back the ionic conditions, which means like it puts out sodium out and then bring back potassium in. The other important phenomenon or concepts are not all depolarization events produce action potential. So for an axon to say fire, depolarization must reach a threshold voltage to trigger an action potential. At threshold, the membrane is depolarized by 15 to 20 millivolts, and sodium permeability increases, and sodium influx exceeds the potassium efflux, and the positive feedback cycle begins. So these are the very important things you need to remember. It's not necessary that all depolarization process produce an action potential, and it does need a threshold voltage, and these are the key features with related to what is happening at threshold level. So there's all or none phenomenon, that an action potential either happens completely or does not happen at all. There's no something called partial happening. It's either happening or not happening at all. That is why it's called all or none phenomenon. So once an action potential is generated, it has to propagate, it has to move forward. So the propagation allows the action potential to be transmitted from origin and downward. That is where it's originated, and it's go further away from it. That's why origin down and along the entire axon towards the terminals. So the sodium influx through voltage gates in one membrane area cause to generate local currents that cause opening of sodium voltage gates in the adjacent membrane area. So it's happening along the adjacent areas since a current is created, as we have seen in a previous slide, and that current leads to opening up of voltage gate sodium ion channels in the adjacent area. And that leads to depolarization of the next area and so on. So once initiated, an action potential is said to be self-propagating. And in non-myelinated axons, when there is no Schwann cells wrapping up around the axon, each successive segment of the membrane depolarizes and then repolarizes. But propagation in the myelinated axons differ, that it's happen in the nodes of Ranvier or in the axonal myelin sheath gaps, not all along the axon, which is why the myelinated fibers, the action potential propagation is much more fast than the non-myelinated ones. So during the propagation, since sodium channels closer to the action potential origin, they're still inactivated, so there's no new action potential is generated at that time during the propagation process. So that will allow the action potential to happen in the forward direction. So there's no new action potential is generated where it's been originated. But there are some exceptions we would see. So here it would show the propagation of the action potential, that the depolarization has happened in this area, the local current has been generated, and it's going to be depolarized this area later and then move forward as it is. So that's what I've been meant. Here it's been propagated, and then the next one, so on. The other important aspect for action potential is that all action potentials are like and are independent of the stimulus intensity. So in the central nervous system tells differences between a weak stimulus and a strong stimulus by frequency of the impulses. So the frequency in the number of impulses received per second, frequency is the number of impulses received per second. The higher the frequency, it said that more stronger stimuli. So in this figure, it shows the relationship between the stimulus strength and the action potential frequency. So here you have a threshold level, over here you have a stimulus, and this stimulus is much more higher. You see frequency is higher with the higher stimulus, frequency is lower with the lower stimulus. There's another important term called refractory period. With related to the refractory period, it's defined as the time in which neurons cannot trigger another action potential. In this refractory period, what will happen is voltage-gated sodium channels are open, so neurons cannot respond to another stimulus. There are two types of refractory period: absolute refractory period and the relative refractory period. In the absolute refractory period, the time from opening of sodium channels until resetting of the channels, that's called the absolute refractory period, and that ensures that each action potential is an all or none event, and it enforces one-way transmission of nerve impulses. In the relative refractory period, it follows the absolute refractory period. Most sodium channels have returned to their resting state. Some potassium channels are still open. Repolarization is happening during this relative refractory period. The threshold for the action potential generation is elevated. There could be like in the relative refractory period, the threshold for action potential generation has been elevated. But the exception is that if you can provide a strong stimulus during the relative refractory period, you could stimulate an action potential. So the key message with this content is that during the relative refractory period, if you provide a strong stimulus, you can generate another action potential. So here you would see the absolute refractory period, the depolarization happen, and the repolarization is happening. In the relative refractory period, starting from here, some potassium channels are still open, and then the hyperpolarization is happening, and during this process, if the stimulus is high, you can generate another action potential. With related to the propagation, we have to discuss about the conduction as the conduction velocity. The action potential occur only in the axons, not other cell areas of the neuron. The conduction velocity in the axons can vary widely. So the rate of action potential propagation depends on two factors: the axon diameter. The larger the diameter fibers, they have less resistance and faster the impulse conduction. As also the degree of myelination. There are two types of conduction, depends, there are two types, myelinated, unmyelinated, and fibers, and also based on the degree of myelination, the two types of conduction depending on the presence or absence of myelin. So it could be continuous conduction or saltatory conduction. The non-myelinated ones perform the continuous conduction. The other one perform the myelinated one perform the saltatory conduction. With related to the continuous conduction, it's a slow conduction that occurs in non-myelinated axon. The saltatory conduction occurs only in the myelinated axons, and it's about 30 times faster than the continuous conduction. And as I mentioned before, the action potentials generated only at the gaps, and electrical signals appears to be jumped rapidly from gap to gap. So here it shows the action potential propagation in non-myelinated and myelinated axons. So here you see the stimulus and the size of the voltage, and here you would see in non-myelinated axons the conduction is slow and voltage-gated sodium channels regenerate the action potential at each point along the axon, so voltage does not decay with time and conduction is slow in this case. In the myelinated ones, you see that it's happened at the gaps, so with one gap and the other gap as it goes on, and it's much more faster. With related to the conduction, we can't forget about the different types of fibers. The fibers can be classified according to their diameter, degree of myelination, and speed of conduction. And they can be fall into three groups. Group A fibers, they are large diameter fibers. The myelinated somatosensory and motor fibers of the skin, skeletal muscles, and joints. And the other type is the group B fibers. They are intermediate fibers. They are lightly myelinated. Group C fibers are the smallest and the unmyelinated. So B and C groups include the autonomic nervous system, visceral, motor, and sensory fibers, which supplies to the visceral organs, so on. The clinical aspect of the components that we have discussed is some of the clinical aspects would be certain diseases with related to nerve conduction and with related to fibers. So multiple sclerosis is a popular known disease, which is an autoimmune disease that affects primarily young adults. They destroy the myelin sheath in the central nervous system. The immune system attacks the myelin, and then this myelin turns into sclerosis. So the impulses starts to become slow, and eventually cease with time. And also the demyelinated axons increase sodium channels, causing cycles or relapses and remissions of these patients. The symptoms of these multiple sclerosis would be visual disturbances, weaknesses, loss of muscle control, so on, and the treatment would be modify immune system activity, as well as preventable causes to be maintained high levels of vitamin D, and it's still in a research level with related to how it reduces with those, how it prevents with related to those. The other important aspect with impaired action potential impulse propagation, it could happen with number of chemical and physical factors. For instance, we use local anesthetics. They block the voltage-gated sodium channels, and it prevents the depolarization happen, so the patient would not feel the sensation of that area. The cold temperatures or continuous pressure interrupt blood circulation and delivery of oxygen to the neurons, and that will lead to cold fingers, like numb or tingling sensation, so on. Yeah. So this is the end of the part 2 of chapter 11, and I will see you with the part C.